I'm going to work through the combustion analysis problem so that it's on one piece of paper and a little neater than the version we did in class. So if you weren't in class, this would be a good way to follow along on this particular problem. This is in your textbook. It's on page 105. So page 105. And the problem, let me see if I can change this light slightly. There we go. It's in view, in focus is what I'm trying to say. It's number 44. Okay, so page 105, number 44. It's what in chemistry we call a combustion analysis problem. Combustion analysis means that we're burning something. So in this case, and we're analyzing the products. In this case, we have a compound that contains carbon and hydrogen and oxygen. And anytime you combine a compound like that with oxygen, you always get the same two products, CO2 and water. So we're burning it. That's combustion. And we're going to analyze these two things and find out the formula for this compound. So we know it contains some carbon, some hydrogen, some oxygen, but we don't know how much of each one. Now we also know that any other hydrocarbon, just an aside, anytime you burn a hydrocarbon, no matter if it has oxygen in it or not, if it doesn't have oxygen, you burn it, you still get the same two products. Okay, so hydrocarbons and oxygen-containing derivatives of hydrocarbons all make carbon dioxide and water. In this particular problem, we're told that we have 0.4039 grams of this compound. I'm looking at that number twice because this is the second time I made this video, and I wrote the wrong number down, just about did it again. So 0.4039 grams, 4039 grams of this compound. So altogether, the carbon, the hydrogen, and the oxygen add up to equal that. We're also told that we have, for carbon dioxide, we have 1.1518 grams. 1.1518 grams. For water, we have 0.2694 grams. Okay, so those are the quantities that were given in the problem, and we're supposed to find three things. Number one, we want to find the percent composition of this compound, which means that we need to know the mass of each one of them. We're asked to find the empirical formula, which means we need to know moles of each one of them so we can get the mole ratio between them. And we're asked to find the molecular formula, which means we need to know the molecular weight and the empirical formula. So here we go. So how do we find the moles of carbon? Or how do we find the mass of the carbon? Well, there's a couple different ways you could do it. In class, we changed this number to moles, then moles of carbon dioxide to moles of carbon, and moles of carbon to grams of carbon. So I'm going to go ahead and do that again and show you how it was done. But another way we could have done it is set up a small proportion like this. We could have said 12 over 44, which will give you the percentage of carbon that's in carbon dioxide. And we could have said that's equal to X over 1.1518. So if you solve the proportion for X, you'd end up with the mass of the carbon, because the mass of carbon is the formula weight of carbon as the mass of X of this compound is the actual mass of this compound. That works. Another way is to take this number, think of it as 12 over 44's percentage, and then take a percentage of that number. So 12 divided by 44 multiplied by that number would give us the mass of the carbon. But we're going to do it the way we did in class, so here we go. So we have 1.1518 grams of CO2. I'm going to double check my numbers. All right, I'm going to change that to moles. So times 1 mole, the grams on here is 44.001 grams of CO2. I'm just going to go ahead and change moles of CO2 on the bottom, change moles of CO2 to moles of carbon. So put moles of CO2 on the bottom, put moles of carbon on the top. One of those is one of those. So I'm going to end up with 1.1518 divided by 44.01, 0.02617 moles of carbon. In a minute I'm going to want to know how many grams, so I'm just going to go ahead and change that now. So I put moles of carbon here, grams of carbon here. 12.01 is 1. So 0.02617 divided by 12, no, times 12.01. So try that again, 0.02 times 12.01. 0.3143 grams of carbon. Okay, so we're going to need to know this number, and we'll need to know that number for two different reasons. We use this number to get the empirical formula. We'll use this number to get the percent composition. Now let's do the same thing for the water. So we're going to take our mass of the water, 0.2694 grams of water. I'll put grams of water on the bottom, put moles of water on the top, so we'll change it to moles. Hydrogen on our periodic table is 1.008 times 2 plus 16, 18.016. We'll go ahead and put moles of H2O down here, moles of H on the top, and you can see in H2O there's 2 H's for every 1 O, so 2 H's for every 1 O. All right, so 0.2694 divided by 18.016 times 2, 0.02991 moles of hydrogen. There's 1 gram of hydrogen for every 1 mole of hydrogen, because this is not diatomic hydrogen because it's in this compound over here, so the Brinkelhoff rule does not apply. So you end up with 0.02991 grams of hydrogen. So now two more important numbers. We need to know the moles. For the empirical formula, we need to know this per percent composition. All right, now we're going to find the grams of oxygen. Because we know that the total mass of carbon, hydrogen, and oxygen was this. So if I said, I'll do this, like I said right here, so 0.4039 grams of compound minus 0.3143 grams of carbon minus 0.02991 grams of hydrogen would give us the number of grams of oxygen, because the compound contained carbon and hydrogen and oxygen. So I subtract carbon and hydrogen, that leaves me with oxygen. So 0.4039 minus 0.3143 minus 0.02991 equals 0.05969 grams of oxygen. Taking a minute to double check my numbers. 0.05969 grams of oxygen. I think that's right. All right, so now we're ready to do the percent composition. So we need to know this number. We aren't ready to do empirical formula yet. There's still another step for that, but we can do a percent composition. So if we wanted to find the percentage of carbon, for example, that's in this compound, you would use the mass of the carbon, 0.3143, divided by 0.4039 grams of compound, multiplied by 100, so 0.3143 divided by 0.4039 times 100, so it's 77.82% carbon. Now to find the percent hydrogen, you take this number and divide by that. To find the percent oxygen, you take this number and divide by that. And I won't take the video time to do that, but that's how you do a percent composition. Now we need to find the empirical formula. So let's go back to the numbers that we have. I'll mark this one in orange. We know this number, and we need to find the corresponding number for oxygen. We see these were moles, and this is only grams, so we're going to change grams to moles, put grams of oxygen down here, put moles here. 1 mole is 16.00 grams. So 0.05969 divided by 16 is equal to 0.003731 moles of oxygen. So now we have our moles of oxygen. So you write your empirical formula down, but it won't be empirical because it's not small whole numbers, but we do know that if I have 0.02617 atoms of oxygen, or moles, if you will, of oxygen, and I would have for hydrogen 0.02991, and for oxygen I'd have 0.003731. So that's our formula, but it's not in whole numbers, and I need it to be in whole numbers. So to do that, you divide all of them by the smallest of the numbers of moles. And remember, these are moles. How many atoms? Moles measure how many atoms. So we'll divide by the smallest one of the three, 0.003731. 0.003731, 0.003731. Here we go. We know this is going to be 1, so that's going to be 1. 0.02991 divided by 0.003731 is 8.02. So we'd say H is 8.02. which we're just going to call 8. And then, because it's really close to 8, 0.02617 divided by 0.003731. And that's 7.02, or just 7. So we'd say C7H8O. And that is the empirical formula. The last thing we need to do is find the molecular weight. We're told the molecular weight, going back over to the book, it says the weight is 108.1 atomic mass units, 108.1. We know that carbon weighs 7, so 12 times 7 is 84. 1 times 8 is 8, and 16. 84 and 8 is 92. 92 and 16 is 108. So the sum of these numbers is equal to that, which means that in this case, the molecular formula and the empirical formula are the same. Now, a couple other little points. Just pretend for a minute that had been 216. If that had been 216, then this would have been C14H8, H16, sorry, O2. If this is twice the weight of the empirical formula, then the empirical formula would need to be doubled. So if that had been 216, we would have had to double everything here. Another thing that could happen to you is when you do these ratios, like this was 7 and 8 and 1, they were pretty neat. But sometimes you might run into 7 and 8.5 and 1. If that was the case, 8.5 is not a whole number, so you had to multiply it by 2 to make it whole. So our formula would have been 14, 17, and 2. We would have had to double all of them to make it into whole numbers, the smallest whole number ratio. All right, so the breakpoints on this type of number is like 8.5 or 8 1/3. You'd have to multiply by 3, or if it comes out in fourths, you multiply by 4. Other than that, we'll round off to whole numbers. All right, so that's that combustion analysis problem. And it's all on one piece of paper and a little less jumbled than we had it in class. So I'll put that on the website and we'll call it a day.